the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to linear algebra students who are currently going through homogeneous linear systems, parametric forms, all that fun stuff, and we're about to glue together actually the idea of a parametric form. We're going to make that parametric solution or parametric vector solution to a system of equations be very important. But before we get there, we have to lay down some definitions. So we'll start with the non-homogeneous linear system. A system of equations is said to be non-homogeneous if it can be written in the form ax equals b, where b is non-zero. Now, that is counter, the exact opposite, in fact, of a homogeneous system, because a homogeneous linear system is one that can be written as ax equals 0. So those are kind of diametrically opposed in a way, but they're intimately linked in another way. So there we go. Ax equals b, where b is non-zero, is non-homogeneous, and ax equals 0 is homogeneous. Remember, the equation ax equals 0 always is consistent. It always has at least one solution, that's the trivial solution. Whereas a non-homogeneous system, it could be inconsistent. So obviously I can't just stop this video right there. There's just too much time left, right? Well, let's talk about the types of solutions for each of those systems. The solution to a non-homogeneous linear system that lacks any parameters or variables is called a particular solution to the linear system. Now that may be really weird for you to understand, so let me be very clear here. We have already defined what a parametric form of a solution is. The parametric form of a solution is a solution that looks like this, where c sub 1, c sub 2, all the way to c sub k are just parameters. They're things that we can adjust. That is not a particular solution. However, what if part of our solution was all the stuff where these were all adjustable, but we had one additional vector there that did not have an adjustable parameter out front? So what if part of the solution was concrete? This does happen actually quite frequently. So if it is the case that you have a non-homogeneous linear system, so a system like this, ax equals b, and pretend for a moment that the vector solution can be written as a linear combination of v1 through vk, and the weights of that linear combination are adjustable, and we've seen this in one of our solutions, so I'll point back to it in a moment, plus some other vector that does not have an adjustable coefficient. Well, that vector, that's the non-adjustable coefficient vector, is called a particular solution. And it's a particular solution because of this definition. It's a solution to a non-homogeneous linear system that lacks parameters or variables. Now, the example that I would show actually is from a homogeneous linear system, so that's not going to really work out very well, but we'll see it in a moment, really building onto this. So that's why I'm doing all this in a single video, is because, well, it's just much easier to see the impact of the meaning of a particular solution if we also do an example. Before we get to that example, we go through one last very important theorem. So important that it is actually numbered in the text that I use, and the theorem is the following. If the system has a solution, that is, if the system is consistent, then the solution to the non-homogeneous system, ax equals b, is the sum of the particular solution, p, and actually in the previous page, I used v sub p. Maybe I should use just p here just to keep my notation consistent. So we'll just say that's the particular solution. Anyhow, if the system is consistent, then the solution to the non-homogeneous system, ax equals b, is the sum of the particular solution p to the non-homogeneous system. And now here I'm going to use a different highlighter because this is kind of where this theorem splits into a secondary part. So it's the sum of the particular solution to the non-homogeneous system and a linear combination of the solutions to the related homogeneous linear system AX equals 0. And I mentioned this in a previous video, that the homogeneous equation and the non-homogeneous equation, while they are disparate, they're actually opposites of each other, they share one very important thing in common. Solutions to the non-homogeneous equation will involve solutions to the homogeneous equation. And that's exactly what this is saying. Every time that you go to solve AX equals B, you will also be solving AX equals 0 and finding that set of solutions as well. Now, the importance of this statement. In oversimplified terms, this theorem is stating that whenever you solve a non-homogeneous system, AX equals B, and this is what I was saying earlier, your solution is the particular solution of the original system, AX equals B, plus the solution to the related homogeneous system, AX equals 0. Now, it's somewhat simplified to say it that way, but it is pretty much true. And as a notational note, we often use the vector P for the particular solution to AX equals B, and V sub H for the solution to the homogeneous system. Now, my voice is kind of hoarse, so I'm not going to burn time on a proof here. However, I do want to do at least one example. Before I get there, I want to give you a little bit of warning. That theorem that we just introduced, that the solution to AX equals B is equal to the particular solution of AX equals B plus a linear combination of the solution set to the homogeneous AX equals 0 equation. But that theorem only holds if AX equals B has a solution. So you can't use that theorem otherwise, but you're not really going to, honestly. It's just worthwhile to state this. So let's see this in action, because I think that an example is worth more than I could possibly write down in terms of theorems or definitions or anything like that. So use parametric vector form, in other words, write my answer as a linear combination of vectors, to describe all solutions of this linear system. Use P for the particular solution and V sub H for the homogeneous solution. Compare the solution to this non-homogeneous system to that of example 1.5 number 1, and we'll do that. Now, because we are online, I can quickly do the row reduction here, but let's go ahead and at least get it into an augmented matrix. So let's do that right now. Now, I want to draw your attention to something before we jump too far ahead. The coefficient matrix, 1, 2, 3, 4, 5, 6, 6, 7, 8, that actually comes from a previous example. That's this guy right here. 1, 2, 3, 4, 5, 6, 6, 7, 8. This is the homogeneous version of what we're dealing with in this new problem. So here's the homogeneous system, and then we row reduced the homogeneous system, and we got down to this parametric vector version of the solution. So that's the solution to the homogeneous equation, or basically the related homogeneous equation to the current problem we're facing. So I wrote that right here. With the homogeneous equation using the same coefficient matrix, we arrived at the following solution to the homogeneous version of this non-homogeneous equation. So now let's solve the non-homogeneous equation. And we get down to this point right here. We've completely used the row reduction algorithm to get to reduced row echelon form. This tells us, this gets us to x sub 1 is equal to 1 plus x sub 3, x sub 2 is equal to negative 2x sub 3, and x sub 3 is free. Now, if I write this solution, it actually has to be broken into two vectors. Notice, all the constant terms, the ones that are not attached to x sub 3, are by themselves. That is, we have a 1 plus 1x sub 3, we have a 0 minus 2x sub 3, and then we have x sub 3 is free, so it's 0 plus some free variable. So 1, 0, 0 goes by itself, it's just a constant. And then everything attached to x sub 3, which is 1, negative 2, and then we have one of these x sub 3's, is right here. Now I hope you notice something about that solution. It's 1, 0, 0 plus some parameter, which I'm going to go ahead and let x sub 3 equal t, so that our solution is 1, 0, 0 plus t times 1, negative 2, 1. And notice something about this solution right there. It is actually the solution to the homogeneous linear system. So when I said earlier that when you solve a non-homogeneous equation, that you're simultaneously, or you're also going to solve the homogeneous equation, really what I was meaning is that you're in the background, you're actually finding the solution to the homogeneous system. When you solve the non-homogeneous system, part of your answer, specifically the parametrized part of your answer, is the solution to the homogeneous equation. Now, I think that's pretty amazing. So our solution can be written this way. X is equal to a particular solution, which actually I'll write this way in red. Particular solution, and that's this vector right here, plus the solution to the homogeneous system. And that's this vector and its parameter right here. That's a really good justification of that previous theorem. So again, I want to drive the point home. The note that I wrote right here is true. Whenever you're solving a non-homogeneous system ax equals b, your solution is the particular solution of the original system plus the solution to the related homogeneous system. It's just that that solution to the homogeneous system is actually going to just pop out. You don't actually have to go to the homogeneous system to solve that. It's not twice the amount of work. It's just as you're solving the non-homogeneous system, you get the solution to the homogeneous system. All right. I think that's enough. My voice is pretty hoarse after recording all day, so I hope you guys have a wonderful day. Be great humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.